Welcome everyone. So in this video we are going to talk about the radical abstraction reaction, and more specifically we are going to talk about how radical mediated reaction can be used to carry out the dehalogenation and also the dehydroxylation, which is a name reaction called Barton McCombie Deoxygenation. Okay, so let's start the video. Generally, how do we form the radicals? So what happens, generally radicals are formed as a result of homolysis. They are formed as a result of homolysis of weakly bonded atom. Weakly bonded atoms or weakly bonded molecules instead of atoms, not atoms, molecules, when they are irradiated either with light or heat or under redox condition. So that is where the homolysis take place. Suppose we have these two atoms. So what happens as a result of homolysis? Each one takes its share of electrons. So we represent radical reactions by a half arrow, which means that everyone is taking its share paired of electron. Okay, so that is how the homolysis takes place. Generally, we have heard about the various radical initiators, okay, like benzoyl peroxide or AIBN. Now let us look at how they help in the generation of the radicals and bring about various reaction. Let us take an example of benzoyl peroxide. So when you subject this benzoyl peroxide to heat or under light condition, so what happens? Since there is a since these are electron withdrawing groups, so what happens as a result of which this oxygen bond, this bond becomes very weak. Okay, because this is pushing the electron in this direction and this is pushing the electron in this direction, so this bond can be easily cleaved. So this is exactly what happens. So this gets cleaves, and what we end up getting is the two molecule of this. Okay, now what happens, the driving force for the reaction is the elimination of CO2 gas, which is exactly what happens. So this bond comes here and this bond comes here and this comes here. So what we release is a CO2 gas, so which drives the reaction in the forward direction. So as a result of which what we generate is the phenyl radical. So it is this radical which then attacks either the alkene or other molecule and bring up or carry forward the radical initiator, a radical reaction. Apart from that, we also know AIBN, which is nothing but this molecule as a isobutyronitride. So this is AIBN. Again, we can clearly see that since when this is heated, what happens is that the reaction eliminates the NO2. So this is exactly what happens in this case as well. So as a result of heating, what we generate is this radical, and this one comes here. Similarly, this one comes here and this comes here. So as a result of which minus N2 is released from the reaction. Here it was minus CO2, and what we generate is this CN radical. Okay. Now we can clearly see here the radical that we generate in this case is much more stable as compared to the phenyl radical. The reason being, since this radical is conjugated with the cyano group, so this undergoes conjugation with the cyano. So we can, perhaps if you are asked to write a conjugative structures, how to write it? So we can simply write it like that. Okay, so this is the resonance structure. Suppose in any of the exam or any of the interviews you are asked write the conjugative structure. So this is how you have to write. Okay, so this is going to be the resonance structure of this isobutyronitride. Now, once this radical is generated, this radical is capable enough to abstract the proton from a weakly bonded atom. This abstracts the proton from weakly bonded atom like tributyl trinoxide. Okay, so this is exactly what happens once you add tributyl tin hydride. So what it does, this radical abstract this proton. Again, the reaction is single arrow, so this comes like that and this like that. and what you generate is this tributyl tin hydride. Now this tributyl tin hydride now can react with various alkyl halides, selenides and other substrates. Okay, so this reacts with alkyl halides or selenides, okay, or other substrates. So it is this tributyl tin radical, and this is how it is generated. Now there is a question that is a very important question that is generally asked, that in number of cases what do we use? We usually prefer the combination of AIBN and tributyl tin hydride over benzoyl peroxide. So this is generally something that is not preferred. There is a reason for that. The reason being, once this radical is generated in the case of AIBN, this radical is much more selective. It does not react, the other sides of the molecule. Whereas once this phenyl radical is generated, this is very reactive. This can attack other positions in a molecule and simply completely, break the molecule. Whereas, as I said, this is good enough. This is not very reactive. This is not very reactive. Not very reactive. As a result of which it only abstracts from the weakly bonded atom. So once you have apart from molecule, once you have this AIBN tributyl tin hydride, you can be rest assured that as soon as this radical is generated, it is going to help in the generation of tributyl tin radical rather than attacking the molecule. So once this tributyl tin radical is generated, it is going to attack the molecule. As such, this radical cyano is not going to attack the alkyl halide or selenide or other molecule. That is why this combination of AIBN and tributyl tin hydride is usually preferred. Now let us look at one or two examples where AIBN and tributyl tin hydride is used to carry out the dehalogenation. Okay, so now let's look at one example. Suppose we have here is this particular bromo compound, and we have taken tributyl tin hydride AIBN, and we take toluene as a solvent and we heat it. So what I said, since what we have, once we clearly know in presence of this, what we generate is this tributyl tin radical, and what it does, it reacts with the alkyl halide. So this is nothing but an alkyl halide. And how does it react with an alkyl halide? So I'm considering this entire moiety as R. So what it does, this is what happens. Okay, as these two radical react, so what it generates is that R radical plus tributyl tin bromide. And once this radical is formed, this radical, then this is more like an alkyl radical. So this abstracts the proton from this tributyl tin hydride. As a result of which, what would we end up getting is the dehalogenated product. So the product of the reaction is going to be this. So this will be the product of the reaction. Now let us take one more example. Now we are given with this particular example, this molecule. So what it says is that in the first step, we are treating this with the tributyl tin hydride AIBN toluene. So one thing is rest for sure, what we have in the molecule, let us look at what are the group. So we have this alkyl bromide, we there have this aromatic halide, okay, this is aryl halide, and we have the COCF3. So we can clearly understand that what this is going to do. This is, we know that AIBN, once the tributyl tin, this radical is generated, this radical is not reactive enough to eliminate this particular aryl halide because of the double bond character in the case of the aromatic chloride and bromide or iodide. Okay, we know that aromatic bromide, chloride, they have this double bond character. So this does not react here. So we can, and this is the alkyl halide. So we can clearly understand in the first step, there is a dehalogenation that is taking place. And in the second step, what it is doing is treatment with the sodium methoxide. So let's just do the first step and see what is forming. So in the first step, we understand that what we get is this product. Okay, and mechanism we understand what is the mechanism. This is how it is proceeding. And in the second step, once this is treated with the sodium methoxide, and we know that sodium methoxide, it is a kind of a base. So what it must be doing, since this is an amide here, and we know that this is an amide, okay, and we know that amide can be hydrolyzed under basic conditions. So what this sodium methoxide condition, what happens, this just break hydrolyzed to give us the amine. So the product of the reaction is this amine, okay, NH. So this is the product of the reaction. This is what we get. Okay, so that is how the dehalogenation conditions can be utilized to get rid of the alkyl halide. Now let us look at one example where we use the phenylselenide. So far we have looked at the example of dehalogenation. Now let us look at one example where dehydroxylation is done. Okay, so what this is the molecule, or this is a sequence of reaction that is given to us. So this particular compound is treated with the phenylsilane cyanide compound in presence of tributyl phosphine, and then further treated with the tributyl tin hydride condition. So we know these are conditions for the radical abstraction reaction, or some sort of a dehalogenation or dehydroxylation is taking place. Now if we understand this reaction, this is nothing but a Mitsunobu reaction. This is a Mitsunobu reaction. So what is happening? And this, what it is introducing this phenylsilane moiety onto the alcohol. We know that in the Mitsunobu condition, we get the inversion of configuration once it reacts with the alcohols. So here there are two types of alcohol. This alcohol is a secondary alcohol and this is a primary alcohol. And we know that primary alcohols are more reactive than the secondary alcohol. So the reaction is going to take place at this OH. Okay. So in the first step, the product of the reaction is going to be this. So you can just go through and see what is Mitsunobu reaction. This is going to be really helpful to understand the mechanism of the reaction. So this is what we end up forming. Mitsunobu reaction is probably one of a very good method for one-step preparation of any alkyl halides from the corresponding alcohols. Okay, so this is what we end up forming. And now this compound A is subjected to the dehalogenation condition, or sorry, not dehalogenation, is subjected to the desalination condition. So what we said that once under these conditions we understand what we form is a tributyl tin hydride radical, and what we said that this radical reacts very well with the alkyl halides, alkyl selenides and other substrates. Now what we have is that alkyl selenide. So this is not going to react with this or OH. So what it is going to do, it is going to selectively cleave this bond. So what we end up getting is this is the product. So what we are going to have, just breakage of this bond. So we are going to have a simply methyl at this particular position. So this is how this reaction can be used to carry out the dehydrogenation. So this is what we have done. We have simply got rid of this OH group and we have a methyl. So what we had is 2 hydrogen, and what we have introduced is 3rd hydrogen here. This is what we have done. Okay, and this 3rd hydrogen has come from tributyl tin hydride. This is this hydrogen that has come from. Okay, so this is what we have done in this case. Now we are going to look at various important ways for carrying out the dehydroxylation, which is namely the Barton McCombie deoxygenation, and we will say how alcohols are converted into the xanthate esters and what are the various xanthate esters in which it can be converted, what is the mechanism of the reaction, and this will help us solve many questions that are usually asked in the exam. So let us look at those examples. So what is generally done is that we have the alcohol, and this alcohol is usually converted into a xanthate ester. So this is something like thiocarbonyl ester. So we can write this on this R dash. This can be a SME group, or this can be a OPH group, or this can be a imidazole moiety. This can be an imidazole moiety, or this can be a thiohydroxylamic moiety. So these are the various R dash groups that are possible at this position. Okay, so this is what we end up doing. Alcohols are first converted into this thiocarbonyl compounds, okay, something like that one, and then they are subjected to the treatment with tributyl tin hydride. So what happens now? Try and see what happens. Suppose this reacts with tributyl tin hydride. So what is the first step of the reaction is this. Once you generate this and this attacks, so what you form is SNBU3 R dash. Okay, so this is what you have. So once you have a radical at this position, so what happens? The driving force of the reaction is the formation of a carbonyl group at this position. So this radical comes back here. Now this bond comes here and this radical is generated. So what you eliminate from the reaction is this thiocarbonyl compound. This is very, very important because sometimes you are asked what is the byproduct for the reaction, and this R dash group could be any of these one. So once you have this R dash group, this is then quenched with the tributyl tin hydride. So this is what happens. Okay, and so what you end up getting is the RH. So in the entire process, what you have done, you have simply converted these alcohols to the simple alkene. So what you have carried out is the deoxygenation. And this entire sequence is known as the Barton McCombie Deoxygenation. I hope this entire mechanism is pretty clear. Okay, so now let's look at one or two examples from this reactions. Now let us look at this particular example. So what we have is this entire molecule having a secondary hydroxyl group. So in the first step, what they have done, they have reacted this with sodium hydride and carbon disulfide and followed by treatment with the methyl iodide. Let us see what happens once we do that. So we have this molecule OBZ and we have this OH. So we know this is a strong base. This is a sodium hydride is a strong base. So what it does, it abstracts this hydrogen. So what we form is the O negative here. Okay. TBDMS. Once O negative is formed, and what we have is the carbon disulfide here. So this O negative reacts the carbon disulfide, and what it does, it results in the formation of oxygen, carbon, double bond S minus. So what we have done, then we have added methyl iodide into the media. TBDMS. Once we added methyl iodide, what it does, this S comes, it attacks the methyl, releases this one. So this is what we end up forming, BZ O S SME, and here what we have is TBDMS. So what we said, and then this compound is in the next step is treated with the tributyl tin hydride and AIBN. And from the reaction we understand this is nothing but a Barton McCombie deoxygenation. So this is what we, through this entire sequence what we have done, we have simply converted this into a thiocarbonyl derivative. This is exactly what I said. So if we look at the first step, this is exactly what we did. This is one of the methods to convert this into a thiocarbonyl. Now under these conditions, so what I said, that simply what you are doing is that you are removing this OH. So this entire OH is going to go. So the product that you will end up getting is this OBZ and TBDMS. Okay, so this is what we do. We entirely replace this by hydrogen. So if we entirely replace this by a hydrogen, so this is what happens. This has been entirely replaced by hydrogen, and other hydrogen is already present. So I mean, there's no point writing it like that. So this is simply the deoxygenation product, proper oxygenated product that you get as a result of Barton McCombie deoxygenation. So this is how you have to do. Now let us look at one more example in which we proceed via thiohydroxylamic acid treatment. Okay. So let's look at this particular example. So what we have is this acid chloride is treated with this particular compound looks pretty fancy. Okay, so what happens? We can clearly see out of acid chloride and ester, which one is more reactive? Of course, it is acid chloride which is more reactive. And what happens is that this is going to come like that. This is going to release the positive charge on nitrogen, and it is this oxygen which is going to attack the carbon. Okay, so this is what we end up getting as compound A. So the compound A in this case is going to be this. We have nitrogen here, and this is, so this is what we end up getting. This is called hydroxylamic, just a second, hydroxylamic ester. Okay, so this is what we form in the reaction. Now what happens in the next step? It is treated with tributyl thiol. Under Tollwyn condition, it is reflux. So here we see instead of tributyl tin hydride, what we have is a tributyl thiol. The role is the same. So what happens is that tributyl thiol, once you heat this one, okay, under reflux, so what it does is that it leads to the formation of this radical. Now what happens once this radical is formed, tributyl, this radical, so what it does, it undergoes reaction with this sulfur. So what you get is, just a second, CO2Me here. Okay, nitrogen, just a second. So you have S tertiary butyl. Now you have a radical at this particular position. So just like the first case, if you remember how in the case of benzoyl peroxide, benzyl radical is generated, this is exactly what is going to happen here. So what we have, once we have a radical here, so this bond is going to come here, this radical is going to come here, and this will generate this radical. Okay, so the byproduct that is going to go out of the reaction is this nitrogen, this particular compound S. So this is the byproduct of the reaction that has gone out. Now what we are left with is this radical. So again, what happens? The driving force for the reaction is the elimination of CO2. So this is exactly what is going to happen. So what we will generate is this radical. Now this radical in the media, what we have taken tertiary butyl. So we have this hydride, okay, or we also have toluene. So what it does, it reacts with this one, generates the radical, and this is the Barton McCombie product that we get. So this is the product of the reaction. So that is how the entire reaction pathway proceeds whenever we go via thiohydroxylamic ester strategy. Now there is one important thing that you should be mindful of. Suppose if in this particular reaction here we have used toluene, since we have toluenes, we are pretty much safe that we got the introduction of hydrogen here. So let us suppose, had we used instead of toluene, had we used CCl4, then what we would have got is the incorporation of a chlorine here. Remember, had we used CBr3Cl, we would have incorporated bromine here. Okay, had we used oxygen in this reaction condition, what we have incorporated is a OH here. So this is something that you should remember whenever you proceed via tributyl hydroxylamic ester strategy. Now in this one, he could have also shown you like tributyl tin deuterated. So in that case, what we would have got is the introduction of a deuterium at this particular position. So these are the few things that you should be mindful of, or remember that what are the exact species that are involved in the reaction, what are the solvents that are involved. So if the solvent is not toluene or benzene, then you can immediately understand. Here it is it is not toluene, it is benzene here. So you can clearly understand what is happening. Generally, the preferred solvent are toluene and benzene because they do not undergo any side reaction. But as we can see in this case, if we use other solvents like CCl4, then we can incorporate the halogen molecule at this position. Now let us just try and look at one or two examples that have already been asked in the NET exam, which is exactly based on the chemistry that I have discussed here. Okay. Now let us look at this question which was asked in NET exam 2017, which is exactly based on the approach that I have discussed. And if you have seen this entire video, then this question is as easy as a pie. So what we have here is a secondary alcohol which is again treated with sodium hydride, CH2 and methyl hydride. So we understand that in the first step what they have done, they have formed this thiocarbonyl derivative. So we understand this is absolutely no secret. So this is what they have formed. And in the second step, now what they are doing, they are taking andodecane, this particular compound, using DCC DMAP. So we understand what does this DCC do. This is a coupling reagent that is used to form the amide or the ester bond. Okay, so this is what is happening in this case. And whatever compound that is formed, it is then subjected to the radical abstraction reaction condition, that is treated with the tributyl tin deuterium using AIBN. So let us try and see what happens. Now the example that we took was with the acid chloride. So here we have an acid and what we have is a SHR, we have this is kind of a OH. So what happens, this oxygen, it abstracts this hydrogen and what we form is the S negative. So there is a reaction between this OH and COOH to form the ester. So that is what happens when you use the DCC, and this is exactly what we consider, that we result in the formation of thiohydroxylamic ester. So out of these four options, only in option 3 and 4 what we have formed is this ester. In other cases is this thioester bond that is formed. So these are incorrect options. You can simply say no to these options. Now out of these two options, we've said that under radical abstraction condition, what we will generate is that we will generate a radical at this position. This radical then abstracts the deuterium. Okay, here what they have shown, there is a formation of radical here which can then attack the methyl position. So this is kind of a fancy option, which doesn't look good. So we clearly understand there is a formation of an alkyl radical and this alkyl radical is quenched with the deuterium. So this is the right option. Okay, so this is how you have to proceed such questions, and they are pretty simple. Okay, so in this video we discussed about the Barton McCombie deoxygenation method, dehalogenation method using radical chemistry, and we understood why generally AIB and tributyl tin hydride methods are preferred with, and we have taken the appropriate examples. And I hope this video was of lot of help for you. Good luck. Thanks a lot for watching the video.